Welcome everyone to this talk hosted by Amazon Game Tech. Today I want to talk about a use case of the cloud in game development that's a little outside of the normal workloads we think of, servers and analytics. Specifically, I'm going to talk about a way that we use the cloud to generate terrain at 16K resolution in about 10 minutes. My name is Mark Bayless. I'm a product manager at Amazon. I've been with Amazon for 5 years now. The first half was working on recommendations on the retail website if you've shopped on Amazon. Second half has been with the Amazon Lumberyard team. For those of you that don't know, Lumberyard is Amazon's free source available AAA game engine. My team, specifically the Cloud Canvas team, is focused on Lumberyard's integration with AWS. So the things that we ask ourselves are, how can we make the cloud easier for game developers, and what are some new ways that the game developers can use the cloud? The cloud is making its way into game development. I say it's making its way. I think it's moving kind of slow. I think some things come to mind when we think about the cloud in game development. First, there are infrastructure, core game servers, core backend, things like analytics, downloadable content. We're seeing a little more in the ops side of things like code and asset repository and build pipelines. And then we're also starting to see some rendering in the cloud. This is especially important for game cinematics, for example. ThinkBox has some examples on their website of game cinematics that were rendered in the cloud. Being part of a content creation tool, though, one of the things that we're wondering is, can we speed up the actual content authoring process? So game companies spend probably a third of their budget on content development. And so how can we use the cloud in those production workflows? There's two benefits there's multiple benefits to the cloud. There's two I'm going to focus on. The first is this idea of on-demand computing. I can get compute resources when I need them and only when I need them. And the second is also the scalability. I cannot get only one machine, I can get tons of machines. So using those two ideas, this distributed computing and the scalability, we were able to apply those to this procedural train generation workflow and see a 60x improvement. So that 60x is awesome by itself, but there's a couple nuances here. First, when you're doing something compute intensive, like procedural train generation on a single machine, it takes that machine. You're not doing anything else on that machine for 10 hours. The train that I'm about to show you took about 10 hours on a single machine. So that's one. Two, one, the 60x is one. Two, by offloading it to the cloud, even that 10 minutes, your machine is free to do what you want with it. And then third, I think this is using tools that you're familiar with. So this is procedural train generation using world machine. So game artists who are familiar with this tool are able to see this benefit without necessarily changing tools. So what I'm going to do actually is I'm going to generate terrain at 16K resolution in about the time it takes for me to do this talk. I'll come back and explain what this is later, but the important thing all right, I hit start. So now I want to talk a little bit about the terrain that we generated. We use World Machine and GeoGlyph to do this. All right, here we go. So this is a 2K by 2K island. We generated the color map, the splat map, and the height maps at 16K resolution. Then we downsampled the height map and the splat maps to 2K to get them back into Lumberyard. If I click on, so as we zoom in, we can kind of see this is demonstrating what the value of procedural terrain generation is, right? You can see the erosion through the things. I could go in there and paint all that myself. That'd probably take forever. So by using procedural terrain generation, I can get all of those nuances automatically. However, doing things like procedural terrain generation it takes a long time to do that. As I said earlier, this specific terrain, when we tried to generate it on a single PC, took about 8 hours. 10 hours. When we tried to do it at 32, we stopped it after 48 hours. So we're kind of forced to answer this question in game development. Do we want to optimize for speed or for quality? I think in all artistic pursuits, this is an issue. These things have an inverse relationship. The faster I want something, probably the lower the quality is going to be. The higher quality I want, the longer it's probably going to take. So on the quality side of things, I have fidelity and size. I think these are becoming more and more important as we talk about immersive, realistic experiences. And something to note here is that procedural train generation and time are not linear functions. So the larger the world, if a world is 4x bigger, it doesn't take 4x as long to generate the train. It actually takes much longer than that. So as we grow, it's just going to exponentially get longer to do these things. On the speed side of things, I have things like deadline iterations. I need to get my content out to players as fast as I possibly can. This isn't a problem just with train generation. We also see it in nav mesh generation, light map making, things like that. So using those two cloud ideas that I talked about earlier, distributed computing and scalability, we made this into a divide and conquer problem. Instead of processing all of the information on one machine, we processed it on as many as we could. So we took one height map, we divided it into quadrants, then we built each of those quadrants individually in World Machine, we built them back together, and then we ended up with our final height map, our final terrain. This concept is the same thing that's behind Hadoop and Elastic MapReduce, if you're familiar with that. Kind of what enables making big data possible. So to productize this, we created this thing called the Compute Farm Cloud Gem. Cloud Gems are tools within Lumberyard to basically, if you want an AWS feature, you can put in your AWS information, click upload, and it will upload all the necessary resources for you. So this is available in Lumberyard. I want to walk through the pieces of it. There's 3 pieces. I'm going to use a horse and chariot analogy throughout. The first is the harness, and this kind of orchestrates that divide, build, and merge that I mentioned earlier. The second is the horse. This is the Amazon machine image, known as AMI for short. So to do this task, I need a computer that has World Machine and GeoGlyph, for example. So this AMI is kind of describing what that machine is supposed to look like, the horse. And then lastly, we have the launch configuration and auto scaling group. These start and scale my task. These bring together the harness and the Amazon machine image. What chariot do I want to take? What horse do I want to take? And how many of them do I want to take? So first up is the harness. This is a set of Python scripts that orchestrates this divide and conquer task. It is constantly pulling Amazon simple workflow, which is just kind of like an event recorder, to figure out what it needs to do next. So the first thing it starts doing is asking, I have this input, do I need to divide this input? If yes, then I'll divide. For this use case, we're dividing recursively by 4 until we have 256 tiles. Once it's done dividing, it'll start asking, are there tiles to build? If yes, then it'll start building them. To do this, we're generating an XML file to kind of run World Machine behind the scenes, and we're running World Machine in a shell on these instances. And then lastly, merging. Once it's done building, it'll start asking, are there tiles to merge? If yes, then it will start merging. So we have this decision tree loop thing happening, but we have it happening on dozens, if not hundreds, of EC2 instances. You can see that at work over here. So essentially what's happening is I have a single input, and then I just keep dividing until I get to the level that we want. And then at this level, we can start building these tiles individually. Nothing has started merging yet, but eventually all these things will come together and give me my final product. The second part is the Amazon machine image. So this is our chariot. So the first concept I need to introduce is Amazon Elastic Compute Cloud. This is Amazon EC2 for those of you who are familiar. This is the service that allows me to have this scalable compute capacity. And we have EC2 instances that are optimized for specific workloads. So this is a compute intensive one. So we're using the compute-focused EC2 instances. If you're doing machine learning or rendering, we have graphics, we have memory, that kind of stuff. And then we describe those instances using the AMI. Essentially, it's taking a picture of what that EC2 instance looked like at a period in time to specify what kind of operating system and Python and applications, all that. Again, for our use case, we need it to have world machine and geoglyph on it. There's also a script that then builds this AMI. So the way that it works is we upload the necessary software to S3, and then this Python script launches an EC2 instance, installs all of the necessary software on it, configures it, then it shuts down that EC2 instance and takes a picture of what its storage volume looked like. And from that, we get this AMI. The good thing about this process is once this AMI is created, it's there forever. So if you're doing this process over and over and over again, you don't need to create an AMI each time. And you can also create an AMI for every use case, like if you had one for nav mesh generation or static light map making, for example. The last piece is our launch configuration and auto scaling group. Like I said before, this kind of brings together my harness and my AMI. So in this case, our launch configuration it specifies the kind of EC2 instance type we want. We want something that is really good with computing. It specifies the AMI we want, the one that has world machine geoglyph on it, and we want it to start running the harness, the thing that orchestrates that divide and conquer. The second piece is the auto scaling group. And this determines how many EC2 instances, how many of these horses I'm going to send into battle, and which launch configuration group am I going to use. So going back to the very beginning about this divide and conquer thing, now that we have a little more info, I kind of want to walk through the process again using all of the stuff that I just talked about. So we have these EC2 instances that are running. They have these AMIs, and we have a harness running on them. We get this height map, and the harness starts asking, do I need to divide out anything? If yes, it'll divide it. Once it's divided to the level that we specify, then it will start building things, which looks like generating an XML file, running world machine in a shell, feeding this input out. And then once there are no longer any tiles to build, it will merge them together. So the way that this looked in a real workflow is first we generated the train in Lumberyard. You don't need to start, you can create your own height map in any of the terrain tools. We started in Lumberyard, and then we took that height map and moved it into World Machine to configure our devices. I don't have World Machine installed on this PC, so I can't go through the devices, but essentially it's a three-step process. We're doing some terrain creation, then erosion and naturalization, and then we're getting more granular and doing area-specific texturing. Once we have that world file, which is the definition of those devices, we upload that height map and the world file to S3. And then we can go in and kind of configure what we want to do. So coming back to this, before I said my team's edict is kind of how can we make the cloud easier, and this is one of these tools. So this is called the Cloud Gem portal. And so we have the Compute Farm Cloud Gem that comes with this plugin in the Cloud Gem portal. The Cloud Gem portal is an application that runs in your S3 bucket. So it's yours, you can configure it, you can do whatever you want. But it kind of gives you the administrative, pretty front end. So instead of just having the services up and running, we actually have the interface that you can interact with these services. So once we have the world file and the height map, we're able to upload these into S3. Specify here just some of our settings, like our recursion level of 4, for example. And then in this, we can specify how many EC2 instances we want to use. I can create a new fleet. Here's kind of where I can specify the AMI I want to use, what EC2 instance I want to use. And then once I have those things configured, I can start running the workflow. And as you can kind of see here, so we've divided, we've built, and now we're merging, and we're on this last step of merging. Once we have the final output, we're able to download it. And so we downloaded the splat maps, the height maps, and the color map, and then we imported those back into Lumberyard. And that is what gave us our final product here. So let's see. All right, awesome. So this is actually done now. So I started the generation of 16K terrain at the beginning of the talk, and so now it's done. So I would be able to download it. So that's, I think that's awesome. So I think that this is really good as we get closer to launching a game, because I need to iterate as quickly as possible. I'm placing objects, I'm finding bugs, and as I get closer to launch, I just need to iterate as quick as possible. So in the time that it would normally take me to do one iteration, I'm able to do 60. This is ultimately going to increase the number of iterations I can do, which is ultimately going to increase the quality of my final product. So what's the big idea? So this is just, I think, a piece of what could be something bigger. So first up, I mentioned the nav mesh and static light map baking use cases. I think the same idea can be applied to those, and anything that's computationally intensive and or can be solved in a divide and conquer method. Second, so since we divided and we created all of those tiles, 256 technically, that gives us the input we need for in-game streaming. We already have those artifacts that we can stream into the game. I think that this can fit into a bigger world generation pipeline. So I know that there is some research going on about procedural city generation, for example. This could be, I update some vegetation way upstream and it automatically pushes and rebuilds my terrain, and I have that within minutes. And then this last piece is, honestly, we aren't sure what all this can do. If you think about big data, for example, or EMR in Hadoop, the impact that something like that had was pretty broad, and it definitely impacted, yes. So we still think that there are areas and arenas that we can search out for this that we haven't seen yet. So that kind of wraps it up. I want to encourage you guys to check out Game Tech. This is just one little piece of Game Tech, but we have a whole bunch more. You can find more at gametech.amazon.com. You can actually get this Cloud Gem in Lumberyard 115. It's released to the public. The one thing I would say is that the Cloud Gem is for a very generic use case and not this terrain-specific one. If you want more info on the terrain-specific one, definitely email me, and we can have that conversation. And then we also have a demo booth in the ThinkBox booth, which is 701. So if you want more info, we have developers and tech artists there. Thanks for coming.